Thank you, and good morning to you all. I'm in front of you as a humble person because I spoke to a lot of your staff members this morning, and I'm really very much impressed by the things you are doing. And I'm also very humble because I'm from a country which is pretty small. This is the Netherlands. It's smaller than Michigan State. We have more people than you, but you should realize that this country is approximately 30% below sea level, and more than 50% of our country is sensitive to flooding. And if you think about the Netherlands and you think about the products of the Netherlands, typically people think about this: windmills, wooden shoes to keep our feet dry, tulips, yes, and finally, what do you think our product is? Dutch students would say wheat, but that's not the thing I wanted to hear from you. That's the Wageningen B-series propellers. Because they come from the Netherlands, and I'm coming from Wageningen because MARIN is this institute. And then the question to you is, where is Wageningen? Now, I'm going to help you a bit. It's over there. And if we just zoom in, it's over there, and this little blob above the G is already our facility. Because if you zoom in further, there we are. And that is our facility. So this is MARIN, our last facilities, testing facilities in the Netherlands. So you see our simulators, you see our large testing basins. But it's of course much more interesting to look inside. And then this is one of the largest facilities we have. It's 120 feet wide, it's 350 feet long, and we can generate at model scale the heaviest conditions that a ship can experience. So this is a picture we made with a drone, and this is why I'm working at MARIN, because this is fun, and we are even paid for it. If you think about MARIN, we have a clear mission, and the mission is making ships safer, cleaner, and smarter, and I'm going to tell you a bit about that today. So this is the title, and I made the first line a bit short: research for the future, and then bridging the gap between design and operation. And we start with the future. I was a chairman last year of a sort of project in the Netherlands where we were developing a sort of future vision for the maritime sector. And we called it Blueprint 2050. It was developed with more than 50 people in our sector. And if you think about this word, blueprint, we have to zoom out from the Netherlands to Europe, to the world, and then if you go to the Pacific, to our blue planet. And that is why we call our future vision Blueprint 2050, because this is our blue planet. And one thing is certain: our future is at the sea. But still, we call this thing Earth, which is a bit strange because we should call it ocean. Blueprint is not the sort of the fixed idea of the future of the maritime sector. In the Dikke van Dalen, which is a sort of dictionary in the Netherlands, it's a design, it's a sketch, it is a preliminary plan. So it's not the final thing, it's an idea we have about the future. So that's why we call it blueprint. And then there's something else. I don't know whether when you listen to these future gurus, they always talk about the dot at the horizon. But we are the maritime sector, and the dot on the horizon is pretty short-sighted because you can still see it. So that is one of the reasons why we call it beyond the horizon. So we should not look to the point at the horizon, but beyond the horizon. And that is why we came up with this magazine, and you can find it, you can freely download it from the internet. So just type in Blueprint 2050 and you will find it. And I will try to explain a bit what we as MARIN, as a research institute, did with it. And we came up with our own picture of the future as a sort of vision of the future, which you see over here. And first, a bit about our mission. The mission of MARIN, if you make it a bit broader, is to make ships cleaner, safer, and smarter, and to contribute to a sustainable use of the seas. And I just want to go over this picture and show you a few of our ideas. And it is a positive picture. But let me first start with this one. Zero emission shipping. So I brought my wife, Hilda, she's over there, and it's over there somewhere, but she's now hiding below the table. But half a year ago, I was with my wife and 2 daughters. I was on the beach in the Netherlands. A very modern beach house, and these are my wife and 2 daughters. And the nice thing about being on the beach and close to a shipping lane is that you can combine your family life with your hobby. And I was really happy because I took my camera there and I was making pictures of all these massive ships that were coming along. One of them was this, and I was really amazed. But then, if I looked further, you see the exhaust. And this is another picture I took, and if you look carefully, you see the yellow sulfur that is coming out of the exhaust. And yes, I know that shipping is the cleanest way of transportation, but ladies and gentlemen, it's not good enough as we do it now. And this was in one of our Dutch newspapers. This is the translation in our Financial Times. Emission of sulfur by the 25 largest container ships is larger than all cars on Earth together. You can debate for a long time about this message. It's probably not exactly accurate, but we should not have this type of headlines in our newspapers. Again, we should do better. And what can we do better? One of the things I think, and this is really far-sighted, is to look to nature, to be inspired by nature. And you see here penguins. And if penguins have to leave the ice or the sea at the most dangerous place on Earth for them, which is the ice hole because the predators are around, what they do, they use their tail, but they push all the air they have out of their feathers, and then they have air lubrication. So that is something we try to do at the moment. So you have dolphin tail or penguin tail propulsion, and below there you see the cavities below a ship to prevent the water from having friction with the hull and having an air cavity below the ship. And the combination, I think, will make shipping much more efficient. We are still in the developing phase of this type of technology. There is actually in the Netherlands a ship that is sailing with it. There are others trying to do this, but I think we should be inspired by nature to make our ship closer to zero emission. This is America's Cup sailing. And we can also let ourselves be inspired by top sport. For instance, leading towards wind-assisted ship propulsion, as you see on the right-hand side. And what we're doing at the moment at MARIN is we are working with the AkzoNobel team in the Volvo Ocean Race to better understand their ship to win the race, but also with computational fluid dynamics, with model testing and with full-scale trials, really understand the complete chain from the conceptual development to the operation. And in the end, of course, we want to help this team to win the race because it's a one design yacht race. And that means that if you really understand your ship best, you can win. But of course, in the end, it's not about winning top sport, but it's winning like this type of things. So I really hope that in the future, this type of wind-assisted ships will be sailing our oceans and will again reduce ship emissions. And if you think about the challenges we have here, it's hydrodynamics, it is aerodynamics, and it's also about the complete system. So wind-assisted propulsion is one of the possibilities. And here you see it with hard sails, but also with the rotating, what is it? I have a jet lag. Flatner rotors, yes. So one thing, and that is wind-assisted propulsion, zero-emission shipping. And we go to the next one, renewable energy and food at sea. What you see over there are floating wind turbines. Around 15 years ago at MARIN, we started with wind turbines, with floating wind turbines. And everybody at that moment said, "You're crazy." At that moment, we hardly did have any fixed bottom-mounted wind turbines in our country. And we had this idea, okay, if you can do it on land, and you can do it maybe at sea, why don't we put them on a floating structure which we know from offshore oil and gas, and then you can do it at locations where you have much more wind, where they're out of sight, and they are very efficient. We were lucky because the University of Maine invited us to be involved in a project for floating wind turbines offshore Maine, and as a result we developed a setup, a very high quality wind setup in our facility, and in this facility we can actually test floating wind turbines where we look to the aerodynamics and the hydrodynamics combined. And now at a lot of locations people are actually developing at full scale this type of turbines. And why I show this? Because this is 15 years ago that we start with it. And sometimes maritime people are very practical. And they like practical stuff, practical solutions. But we also have to look to the future and do the daring stuff. Talking about that, and I will be short about it, one of the things a lot of people talk about is autonomous ships, autonomous shipping. So all hands on deck will be zero in the future. So you have autonomous ships, but you still have humans on their shore control center, and people are also looking to platooning and the whole interaction of ships. As MARIN, we try to contribute a small part to it. And one of the things we can do is to contribute the experience we have with the big data analysis we do on AES analysis. So what you see on the left-hand side is an analysis of near misses at the North Sea. Some people think they look like spermatozoids, but you can see how ships are in reality reacting on other ships. And with this type of knowledge, we can develop evasive algorithms for autonomous shipping in reality. Because, yeah, this is really funny, so I'll run it again. But of course, in the end, all these autonomous ships, they also have to sail in areas where you have normal ships. And that needs to be done safely. And then to something completely different. Floating ports and cities. I'm from the Netherlands. Actually, I'm from a village where we invented dredging. So in the Netherlands, when there's a problem with sea level rise, we have one solution. That's called making the dikes higher. And I think it's a bit short-sighted again. So I have one colleague, this is Olaf Waals, and he came up with this idea of a floating mega island. Because in times of sea level rise, you can make the island sort of float so that you prevent problems. Just to give you an impression, this here is an LNG carrier of around 600 feet, 700 feet long. This island, at model scale, around 8 by 6 meters, but in reality it's 3 to 5 miles. And it contains of 87 triangles which are coupled. And what we are doing here is testing it in our offshore facility. This is at scale 1 to 250. And what you see here is this island in 15 meter significant wave height, a 12 Beaufort storm. And I will run it again. We were actually amazed by what we've seen. Because you should realize 15 meter significant wave height. And if you just look to the front, you see, yes, this is moving. But you should realize this is in reality the beach. But if you look here and you look here, even in a 15 meter significant wave height, the motion of the center island was only 1 degree. So we think that this is a solution for floating ports, maybe for floating islands to live on. And then if you just look to this one, this is a picture developed by Wärtsilä, the Finnish company, and I really like this because just see their future vision. You see renewable energy at sea. I hope these are floating wind turbines. This energy, electric energy, is brought into hydrogen, which is stored on a floating port, which is then transported by autonomous vehicles, maybe even underwater, to all around the world. Now, as a naval architect, I'm happy when I see this type of pictures, and I hope you are. And then my question is, how do we, me as president of MARIN, my people, and you contribute to this type of future world? Let me please take me to the start of my career at MARIN. Exactly 26 years ago, a young guy from Delft University joined MARIN. And our Royal Navy had some money left, and they had frigates called the S frigates, and this is the picture, and it had one problem, and that was the problem of green water. So they asked to this young engineer called Bas Buchner, can you please do a model test to better understand the physics of green water? So this is my very first model in life. I designed it, my people made it, and I started to do testing. Unfortunately, all the videos of the time, actually there was video already 25 years ago, were gone, but I'm going to show you a picture of green water on a US Coast Guard cutter. So what you see here is a green water problem. What is green water? Green water is the massive water on the deck of the ship in high waves. And it is a problem where the motion of the bow going downwards, is out of phase with the wave motion, and then you see that you get massive water on the deck. Just look to the barrel of the gun. This is at model scale, but you should realize at the time that I was doing these tests, the shield of the gun of the ship was quite regularly damaged as a result of green water, and it was designed for normal blast. So you can realize that green water is a large problem. This was my first project, and then I went into the offshore oil and gas world. So I started to work on FPSOs, floating production, storage and offloading units. So you see some of the experimental work and some of my early CFD work. Water that comes onto the deck, focusing, having a high velocity, and then hitting a structure. I did model testing, I did CFD, and this is, to be honest, the status at the moment. One of my colleagues made this recently. This is a moving FPSO. Actually, the motions are coming from the model testing, and then with our CFD code within MARIN, we are able to calculate this at the moment. And the funny thing about writing your PSD is that sometimes people call you when they have a problem. And at a certain moment I was called by the people from owning this Vark FPSO. Because this Vark FPSO, a Norwegian FPSO, was in a heavy storm and they had a problem. So what you see here is the front here of the deck house, and they put the deck house on the bow of the ship, and at a certain moment there was a storm and the people were sitting in the canteen. You should realize this is the canteen, this is not a deck level is here, so all the portholes were closed here, but they thought they were safe sitting there in the canteen having their lunch. But at a certain moment somebody looked out of the window and said, "Look, a wave!" The wave hit the front of the deck house, pushed in a window, and they were sitting in the water together. And then they came to me and said, "Do you have an explanation?" I think I do. If you just go to this research, you see here green water coming onto the deck. So you see the water flowing onto the deck, you see a high velocity flow hitting the structure. And what you should realize, if you look to this, there is a balcony here at this level. You should realize this is a balcony approximately at that level. That means that the water is hitting the underside of the superstructure, it's shooting high up, and then it is captured below the balcony. And as a result, and you can also see it over here, you get the high pressure, and as a result, this window was pushed in. Funny thing is, the window didn't break. No, the bolts of the window frame broke. But then there is the comment of the crew. Because the crew wasn't very happy with our designs as naval architects. Because this was their comment. It was in Norwegian, but I don't understand Norwegian, but this is the translation. What did they say about us? This ship is designed by farmers, no by inland farmers. And I think they were right. And that is one of the problems because, and I have to say, green water is a very old problem already. The oldest reference I know is from the Bible. If you look to Matthew 8, verse 24, the famous storm of the story of the storm at the lake. And behold, there arose a great storm on the sea, so that the boat was being swamped by the waves. Actually, this is a picture of the famous Dutch printer Rembrandt. As I have time enough, I think. There was, for a long time, there was a theory why in the 17th century the Dutch painters were so famous. It was really a serious theory by the people, the scientists. And that is because they thought the Netherlands is below sea level, and that will change the brains of the people. And they thought that because we were living close to the water, our brains became like sponges. Seriously. And because these sponges could sort of take pictures better into their brains. But but again, Rembrandt was a good painter, and he made this very nice painting about the storm at the lake. But if you look to the first developments of FPSOs, they look like this. At that moment, the offshore engineers, they took the superstructures they knew from the fixed structures above the waves, and they just put them on top of the deck of ships. But if you just go to the internet and you look around to what's happening on normal sailing ships, you see this. And again, the message is here, you should take into account the experience, the operational experience. And a few years later, FPSOs from the same company look like this. So a bow which is 5 meters higher, everything much better protected. And also, if you go to naval shipping, things like this show you that green water is a problem we know for some time already. And I think this is one of my major messages. If you really want to predict the future of your ships well, you have to link CFD simulations, model testing, and full-scale trials. And for a long time, we sort of splitting this type of technologies, but I really believe that they all have separately added value, and that we should link, we should sort of, like the painters were doing, we should digest the experience for people sailing at sea and include that in our designs in a better way. Just another example which is quite exciting to me are free-fall lifeboats. I can tell you we did more than 10 million euros in the research of free-fall lifeboats, and I'm going to show you why. This is a tryout of a free-fall lifeboat in real life a few years ago. You can find it on the internet. It looks like a sunny afternoon. There were people inside. But they came out safely. But you should realize these boats are there for the safety of people. And if you look to this problem, we have to make sure that people who are on a ship or on an offshore structure that can get on fire or can explode, they need this type of equipment to safely depart. And then we can do a few things. The first thing we can do is full-scale trials. This is in the port of Amsterdam. There can be 50 people inside this boat, and we do full-scale trials. And the first question is the boat strong enough? The second question is it able to get away from the platform? And finally, are we as people strong enough? So you see it here again. So 1, is the boat strong enough? 2, are we strong enough? And 3, is this boat able to get away from this burning ship or platform? Now, amazing hydrodynamics, but here you can see that this type of boat in calm water is able to get away. But imagine that the waves are coming to your platform. Is it still able to get away from this platform? And you cannot test that at real life, so that is what we do here in our facilities. So this is in waves, so you see waves coming in, you see the ship falling in, and here, slow down to real scale. And then you see that because it's falling into a wave, it's almost dead into the water. And you can imagine that the next wave brings it drifting back to your burning platform. Another example here. Here it's falling in the front of the wave. Here you see the underwater video. And what you can see here, this cavity behind the freefall lifeboat, it's filling. I will run this again. It's quite interesting just to follow. If you just look to the back of the freefall lifeboat, you see there's a cavity which is filling quite rapidly, and you see an impact. And this impact sometimes is pushing in the back door. So quite often the back door is pushed in. And finally, here you see it in our CFD calculations, and you see the main physics, including a big fountain which is a result of this impact at the back. So again, if you look to this, if you really want to make this operation safe, you should make use of your calculations, time domain simulations, or CFD, model testing, and full-scale monitoring. We also wanted to apply this type of methodology for the problem of sloshing of LNG. So you see an LNG carrier, you see the containment system, which is stainless steel with foam and wood behind it. But then there's one big problem. You can do calculations, you can do small-scale testing, but nobody is allowing to do full-scale measurements on LNG. So I had one smart colleague, and he came up with this idea to do a full-scale test, but then with water instead of with LNG. So we went to a big flume of one of our colleague institutes. We actually took a full-scale sample of the containment system, and we were sending waves to that containment system, sort of representing the sloshing that can happen inside this tank. So you see this containment system, stainless steel, a few millimeters thick. You see the wave generator of the flume, and they are sending a focused wave towards this containment system. So you see the complete wall, scale 1:1. You see the project manager, a MARIN guy. He's enjoying his work. And here just note to the vibration of the wall. But, let me stop this for a moment. I don't know whether you noted, but inside this flume there was a big window. And through this window we studied with high-speed video the details of the impacts. I'm going to show it to you. Just look to the shock wave that occurs at the moment that the impact is there. See? The funny thing about this video is I can show it to engineers like yourself, to scientists, but also to politicians. They all become quiet. So shall we do it again? So if you really want to show to people that you're working in an interesting field, you can have this video from me. Just look to the pressure cells which are actually in this area, and here you see the time traces of the pressure. So even in this very small area you have a huge variation in pressures. What we also did is we put a camera also at the back in the containment system, And then you see the deformation of the structure. So this is the same structure at the impact, and here you see the deformation of the structure at that moment. Show this one again. So you see just at the moment of impact, you see very high velocities going up against this corrugation, and this is really deforming. So based on this research, we learned a lot about full-scale impacts against this containment system. But there's one difference between water, actually there are more differences, but the most important difference between water full-scale in this impact and real life is the fact that LNG is a boiling fluid. And that is a difference. So what we are doing at the moment is developing this flume. So we are developing a flume which is around 45 feet long, around 3 feet wide. And what we are doing here, we're putting this flume in what we call an autoclave, and you can close that, and then actually you can bring that complete system to a temperature of 200 degrees Celsius. That means that the complete water in this flume is boiling, and then we are going to repeat the same type of problems, of the types of impact tests. And just to show you how large this is my colleague Hannes Boga, the guy who is doing this research at MARIN, and he is making preparations. So this is the autoclave. The flume is not inside yet, but just want to show you the size of this type of stuff. So in a few years, I hope I can come back and show you this type of nice videos of the new setup. Okay, LNG sloshing. But then I became involved in the issue of LNG offloading. In recent times, Shell developed this floating LNG plant, Prelude. It's 470 meters long, it's 70 meters wide, and at a certain moment they came to us and said, can you please predict up to what sort of conditions we can still be moored alongside this structure to do the offloading? Now within MARIN, we did our diffraction analysis, we did time domain simulations, we did model testing, we actually measured on board, and we were able to say with quite large accuracy that you could do this in 98% of the cases up to significant wave heights in the order of 2.5 to 4 meters wave height. But then we realized that this wasn't enough. And what we were missing is the crew. Because if you imagine that you have to do this operation in 2.5, 3 meters significant wave height, you become scared. So what we did in this type of projects, we brought the people onto our simulators, which were developed to bring ships safely into port. But in this case, we developed in the simulator the LNG FPSO. We put in on our large simulator, we put in the LNG carrier. We brought in the tug crews, and we allowed people to experience these very complex operations. In the beginning, they were saying, no, we are not going to do this. This is not safe enough. But by helping them to understand the operation and to change the operation in such a way that they were willing to do it, in the end, Shell has its system doing side-by-side offloading. And I know this is painful, but also in your Navy, you should realize that the human factor is extremely important. So recently on the USS John McCain, the human factor is sometimes forgotten in our field. And that is one important lesson we learned at MARIN recently. Our focus for a very long time was just at the ship. But we really should focus on the ship and its crew. And simulations and simulators really help us to make progress in that. So if you look to MARIN's, let's say, approach, it really looks like this. So we want to be involved in concept development, in design and operation by linking our simulation tools, our testing tools, our simulators and our monitoring. And to show you this type of thing, what you see here on the right-hand side is the development of the port of Rotterdam, where they were bringing in these large, more than 20,000 TEU container ships. In this type of large ports, they were developed for much smaller ships. So this whole operation, including all the tugs you need for that, you have to bring in the people, the pilots, the people on board of the ships, on board of the tugs, to make sure that this type of operations is done safely. And we were recently working on this new ship, the new aircraft carrier of the British Royal Navy, and they have a very big ship. They completely changed the port of Portsmouth to make sure that this ship was able to enter port safely. But again, they needed to train their crew to make sure that actually this could be done. So you see here the ship in our simulator. Here you see the people on the bridge. So you see the pilots, you see their first officer, and you also see their commander. And the British, they're very good in summarizing the essence of things, because their commodore, the commander, at the end of the training said this: the simulator stimulates cooperation, competence and confidence. And I think this is really the key of involving people in your future design. One of the recent things we've done at MARIN, let's say in this field, is developing things for complex operations at sea. So what you see on the left-hand side are the fast ships of our Royal Navy. You see on the right-hand side model testing in very complex conditions. And you should realize the people sitting on this type of fast ships, 40 knots, they experience G-forces in the order of 8 to 10 G. And their trainers, they have to experience this type of acceleration levels every day. That makes them sick. So what we have developed at MARIN is this. This is a moving simulator. And actually the basic technology from this moving simulator comes from Formula 1 racing simulators. We made it a bit bigger. We put all the equipment of the real fast ships of our Navy on it, and we started to sail. So what you're going to see now is me with Admiral De Waard, one of our admirals in the Netherlands. And here we are checking a ship still in nice weather, but then with a click of a switch, my colleagues can put in heavy weather. The funny thing is you can't stop smiling when you're on this thing. But I can tell you, even the toughest Marines, we can get seasick on this machine. So, but of course, in the end, the real reason to do this is to give them a very efficient training, to make them well prepared for their missions. And of course, you have to combine this not just on the small ship, but also include all the large ships around them. So it's not just the small ship, the small simulator, but also the people being on larger simulators, working with them from the large bridges. So again, for this problem, simulation, desktop, model testing, moving simulators and monitoring to link the concept development to the operation. Finally, what is the strength of a simulator? I think it's this. Do you know what this is? This is the pause button. And it also has a rewind button. And the strength of a simulator is that you're allowed to fail, and as a result, you're allowed to learn. But that means that you have to develop very realistic simulators to make sure that they actually represent reality. Now, last year, 2 years ago, I was in the plane. Who saw the movie Gravity? A lot of you. This is the type of movie you look when you're in a plane. And I forgot the real name in the movie, but Sandra Bullock and George Clooney were there. Something was going wrong in space, and in the end, Sandra has to go back in a Soyuz, a Russian module. And George Clooney is going to die, and then, just before that happens, there is a very important talk between them. He asks, have you ever flown a Soyuz? She responds, only on a simulator. He says, then you know. But she responds, I crashed it always. And then he says, it's a simulator, that's where it's designed for. And then he dies. But this is the essence of using simulators. You're allowed to fail, and as a result, you're allowed to learn. So, to make sure that this complete link from concept development through design to operation is made, MARIN is developing a new simulator center. And on present-day simulators, you are allowed to look around, so they are in a cylinder. What we are developing at the moment is a simulator with half domes or full domes, so that you, from the bridge, you can also look up and down. So this is a small dome, for instance, for a small tug. You see at the back, you see also another moving simulator, but if we go inside the simulator, and we call it the 7 Oceans Simulator, SOS, and then it looks from the inside like this. So you can look around, as you can do on normal simulators, but you also, because you're projecting in a dome, you can also look up, and you can look down. And looking down is extremely important, because if you're on a bridge wing and you want to enter a port, looking down gives a lot of additional information. And one of the final things we can do in this simulator, and then I really close my talk, is measure on humans. So what you see here is actually an operation with a small tug guiding a large ship into the port of Rotterdam. But what you can see here, we are measuring the guy's brain activity. And I'm going to show this, maybe you can even hear it.
Daniel, we start phase 2. Pay out to 35 meters and then pull 20 tons. Aye, aye.
The funny thing is, if you look carefully, what you see here is a combination of his brain activity with the towing line loads and the motions of the tug. We are still analyzing this data. It is not easy, but doing this type of measurements makes sure that you can actually investigate the behavior of the people on the board of the ship and make sure that in the end they can do their work properly. Okay, a final summary of MARIN's sort of strategy. What is very important, I think, is that we have to keep in mind the final objective of our institute. And I think also you should take into account the objective of your university. When you're a naval architect, your final objective is not to develop knowledge, but to develop knowledge for better ships. Where does it start if you want to achieve this? First, very good people. And that is why you are at this university. Then at MARIN, we have selected 5 topics where we say we really want to be the best in the world in this type of topics. Sustainable propulsion, waves, impact and hydrostructural effects, maneuvering and nautical, seakeeping, ocean engineering and renewables, and autonomy and control. Beside that, you need key enabling technologies: computational fluid dynamics, measurements and big data analysis, time domain simulations, and, as I mentioned in my talk, operations and human factors. And in the end, and that is very important, and I hope I made it clear, you should link all these tools, CFD, time domain simulations, which will step by step take over from model testing for simple aspects, model testing for complex issues, simulators to bring in the human factors, and finally monitoring, because the proof of the pudding is in the eating. So, my conclusions. Our future is at sea. Clean, safe and smart is our objective. Research is essential to achieve this objective. All methodologies contribute together, and we should not forget the human factor. Thank you very much.